I'm Shubhan Kumar.
Hi, I'm Amol Lokia,
I'm Matthew J.
I'm Sahash Patel.
and our project was Packet Plane. Our objective was to design a small RC aircraft for rapid deployment. Today we're going to show you an assembly video of our best time of 42.5 seconds, as well as have a live assembly for you, where we try to beat our time. We'll do our best in these suits. All right. This is a fully assembled plane, and somehow we were able to beat our previous time.
In our presentation today, we're going to be going over the practical applications of our plane, some of the aerodynamic theory and background behind it, how we designed and constructed it, and finally, the results of our project.
A real-world practical application of our plane is as a support drone. Support drones are equipped with cameras and are predominantly used by the U.S. Army to track terrorist organizations such as Al-Qaeda. However, these are usually too large and unwieldy. Our product provides a solution to that. It's a smaller drone that's better for ground troop operations. The Red Cross would also like to use smaller drones in disaster relief operations. Our initial specified goals were to have the parts of the plane fit within the box, which is 12.5 by 7.5 by 4.5 inches. Also, rapid deployment with assembly time of less than 2 minutes was also achieved. Our optional goals included a weight of 16 ounces and a maximized wing size of 42 inches.
So before going into the details of our plane, we'd like to talk about the aerodynamics behind flight in general. So there's 4 forces that govern the flight of any plane. The weight is simply the force of gravity pulling down on the plane. The thrust is the forward force provided by either the propeller or the engine. The drag is the resisting force provided by friction with the air or disruptions in the airflow. And the lift is the elevating force, and this is caused by differences in air pressure below and above the plane. In addition to this, we have 3 axes of rotation on the plane. So the roll axis allows the wings to go in opposite directions and complete a roll of the plane. The pitch axis allows the plane to tilt forward and back, depending on the vertical movement of the horizontal stabilizer. And the yaw axis allows the plane to spin, depending on the left and right movement of the vertical stabilizer. In addition to this, every plane has 3 main parts. The fuselage or body connects all the parts of the plane together. The wings are mainly responsible for providing the lift on the plane, and the tail, which is made up of the horizontal and vertical stabilizers, provides a steady flight. The control surfaces are hinged sections that are located on the wings and tail, and these are able to be controlled by the pilot in order to maneuver the plane in the air. The ailerons provide the roll of the plane, the elevator provides the pitch, and the rudder provides the yaw. And in addition to this, there's flaps on the wings sometimes that tilt downward and provide additional lift and drag on the plane. These flaps are mainly used in larger aircraft. And it's also important to remember that not all the control surfaces are necessary on one plane. You can use a combination of 2 or 3 of them and substitute for others. So when designing our wings, we kept 3 main calculations in mind. First was the wing loading, which is the weight of the plane divided by the wing area. And the wing loading is directly related to the minimum speed the plane must maintain in order to stay in flight. So for a glider style plane like ours, we wanted a wing loading of about 8 ounces per square foot. And the aspect ratio is the length of the wingspan squared divided by the wing area. The aspect ratio determines the stability of the plane in flight. And again, for a glider like ours, the aspect ratio, the target was a 6 or greater. And the final calculation was the angle of attack. So the angle of attack is the angle at which the wing meets the oncoming air. So by changing this angle, you can maximize the lift on the plane. But once you reach the stall angle, you've already maximized your lift and can go no further. An important component of the wing is the airfoil. So the airfoil is the cross-sectional or side view of the wing. And by changing the shape of the airfoil, you change how the airflow goes around the wing, thus changing the lift. In different environments, different airfoils are more or less appropriate. And the Reynolds number is what quantifies these environments. So after combining multiple factors, the Reynolds number gives one value to determine the conditions that the plane will be flying in. For a plane like ours, 60,000 to 80,000 is the Reynolds number, which is relatively low.
Plane prototyping. This is the process that we actually went through to design our plane. We began by researching different model aircraft and industry designs to come up with our first conceptual model. After that, that conceptual model underwent a period of optimization, which resulted in our final design. That final design, we dimensioned the final design and then modeled it in a 3D CAD software called SolidWorks, so we'd have a blueprint to work off of for construction. Now for the image on the left here, that's a cross-section of the fuselage. You'll notice that there's a hole at the top. The hole at the top houses the main carbon fiber tube, that's the backbone of the entire plane. Below that is a square hole, which is the cargo, which houses the electronic assembly of the plane, which powers the entire plane. The image on the top right is of the wing. You'll notice that there are two rods sticking out of it. These are carbon fiber rods that insert into the fuselage at an angle. And there are also magnets at the same end of the plane, same end of the wing, that help secure that connection. And the image on the bottom right is simply the KFM2 airfoil that we used. The image on the left here is of the horizontal stabilizer. You'll notice that there are creases at either end here. That's because the horizontal stabilizer is 15 inches long, and since our box is only 12 inches, 12.5 inches long, they need to fold in order for it to fit into the box. And the image on the right over there is just the vertical stabilizer. It has a dorsal fin design to maximize surface area while maximize the surface area of the tail. And finally, this is an image of the fully assembled plane. Since the theme of our project was compact disassembly, this is how the plane comes apart. As mentioned, the wing comes out of the fuselage. It also has a crease here so it can fold in two and also fit in the box. And the vertical stabilizer simply pulls out, and the same with the horizontal stabilizer. This carbon fiber tube telescopes back into the fuselage, and then all the parts fit nicely into the box.
So after we completed our designing and modeling phases, we moved on to construction. As you can see here, this is a picture of our folded wing design that's held together with tape hinging. The ailerons on the wing are beveled at a 45-degree angle with an X-Acto knife, and they're attached to the wing using a double-sided tape hinge. This allows the ailerons to move up and down freely. The KFM2 airfoil, as you can see here, we double-layered the Depron foil on the front and single-layered it in the back. This created a 12mm layer in the front and a 6mm layer in the back. Additionally, we sanded down the front leading edge of each wing in order to allow the plane to cut through the air more freely. As you can see here, this is the carbon fiber tube that attaches two parts of the wing. It's attached inside of a slot so that the wings can snap into place and be secure. As mentioned earlier, the carbon fiber rods and the magnets were attached inside of the wing so it would fit flush into the fuselage. As far as the tail construction goes, the horizontal stabilizer has a permanently mounted carbon fiber tube on the bottom. This attaches directly into the fuselage. Additionally, the elevator on the back is attached with a similar double hinge tape design as the ailerons on the wing. This allows the elevator to move freely and creates the pitch of the plane. For the vertical stabilizer, with its dorsal fin design, we cut it using a hot wire cutter as well as sandpaper. The two vertical pins drop down straight through the horizontal stabilizer and into the fuselage. The final piece in construction was the fuselage itself. This was created in a two-part design, the front half being pink insulation foam and the back half being carbon fiber tubes that could telescope within each other. The front half was created in a split-piece design to incorporate wooden formers to allow the wings to come in and sit at a 7-degree angle. Final piece in construction was a detachable hatch on the bottom of the plane. This hatch allows easy access to the mechanisms inside the plane and was created using a balsa wood locking mechanism on the front and magnets in the back. In addition, the hatch detaches upon landing to absorb the impact of the plane.
After building the skeleton of the plane, we had to insert the electronic assembly which actually powered the plane. Of course, there's a battery which provided electricity to all the parts in the electronic assembly. In addition, there's a receiver which took transmissions from a remote control on the ground, and that relayed messages to the electronic speed controller and the servos. The electronic speed controller took the message and passed it on to the motor, which controls how fast the propeller spins, which in turn controls the speed of the plane. The messages sent to the servos control the movement of the ailerons and the elevator, which controlled the direction of flight.
So here we have a video of our third test flight. The bigger screen is going to be a third-person view from the ground, and in the bottom right, you'll see a view from the camera that we mounted on top of the plane. So the initial jerking motion you see is because of the throw launch that we employed. This provides momentum to the plane without requiring any excessive landing gear. At a height of 50 to 70 feet, you can see the plane quickly stabilizes. That's because of the 7-degree angle, which we call a dihedral, and the large wing area. And when the plane's turning, notice how the wings go in opposite directions. That's the roll of the plane. By using the ailerons and elevator to turn, we eliminated the need for a rudder. Right there you see the plane kind of hover in the air. That's because due to the low wing loading of our plane, we had a very low minimum airspeed. And when the airspeed matched the speed of the wind coming against it, the plane hovered in place for a few seconds. This was a completely controlled maneuver and actually displayed the maneuverability of our plane.
What you see here is actually the third test flight of our plane, and this was the first test flight in which we mounted the Mobius action cam on top. This camera, of approximately 2.4 ounces in weight, increased the total weight of the plane from 13.6 ounces to 16 ounces. Because we mounted the camera on the center of gravity of the plane, this increased the stability greatly and allowed the plane to be stable throughout its flight.
So now when it's time to land, you'll notice that the pilot simply cuts the propeller of the plane. This allows the plane to use its large wing area and the gliding style we designed to glide to the ground and have a low impact crash. And you've noticed that when it crashes kind of hard, you can see the kind of force of the plane hitting the ground. This was absorbed by the detachable hatch on the bottom, so therefore no components of the plane were damaged. And this was all planned, so we were very satisfied with this test flight.
Over a series of 3 test flights, we achieved a total flight time of 3 minutes and 5 seconds. Our average elevation was around 60 feet, and even during windy conditions, we were able to effectively maneuver the plane. We met and exceeded all our objectives. Our goal assembly time was 2 minutes, and we consistently assembled the plane in less than 50 seconds. Our best time before this was 42.53 seconds, as we said before, and also all the parts were able to comfortably fit within the shoebox. We even met our optional goals of a weight of 16 ounces and a maximized plane size of 42 inches. It's important to remember that this is a proof of concept prototype work, and possible improvements to our final model include a carbon graphite body which would be lighter and stronger, a larger battery for longer flight missions, a larger motor for greater area coverage during scouting missions, and an exploration of new airfoils for this new final model. Overall, using aerodynamic concepts, our design and construction processes, we were able to effectively construct a prototype that met and exceeded all our expectations.
So we'd like to thank some people without whom this project would not have been possible. Our mentor, Ravi Bauer, our research advisor, Liz McGinley, our group member, David Tian, Director of the Governor's School, Dr. Eileen Rosen, Assistant Director of the Governor's School, Dean John Patrick Antoine, our special advisors, Mr. Jim Vagani and Jonathan Holzager, the New Jersey Governor's School for Engineering and Technology itself, and all the gracious sponsors of our program. We'll now entertain any questions.
If this plane is used in military operations, the rival party can bring it down. So in that case, maybe they can copy or whatever, right? When the US launched at Rome, Iran was able to successfully make it land, sometime back. So are there any considerations such as those, or will it have some kind of self-destruct feature?
So basically this plane is designed to be a very small support drone. Not only is it very difficult to shoot down because it's so small, it's only a weight of 16 ounces and 42-inch wingspan. It's also very portable and it's only a support drone. It doesn't contain any sort of classified sensitive technology. It also doesn't contain any sensitive information. All the information it would contain is about the enemy that they know about themselves already. So it's basically just support technology designed to get us intel. If it gets shot down, we don't get any intel, but there really isn't that much of a risk. If our enemy managed to replicate this item, we already know the schematics of it, and we can easily deal with it.
And when designing this plane, we were focusing more on the support drone concept, so a scouting drone, rather than the details of the military application. So this scouting drone can be used in the military, but it can also be applied in disaster relief situations where the Red Cross goes into an area that's devastated and they need to see what's happening. So we would provide this prototype to any, anybody who's interested in researching it, and the military would be able to put in their own technology and advance it, like Sherman said.
Any further questions? Yeah, go ahead.
How come there's like at the tail there's a flap at the back of the tail?
Actually, the flap at the back of this is called the elevator, and the elevator, when controlled by this, it moves up and down, and it makes the plane, it controls the pitch axis. That means the plane moves up and down. So when you saw in the video, the plane went up, that's because this elevator was controlling that.
What material did you use to make the wings?
Alright. We used actually Dacron foam to make the wings. It's a very lightweight and durable foam, and we thought it was perfect for this because it's lightweight and also fits all requirements.
What's the payload capacity for the drone?
I'm sorry, can you speak
What's
up?
the payload capacity? What's your maximum capacity? that you
Oh,
can carry?
actually, this is not a payload plane. It's a scouting plane specifically. All it's designed to do is take camera footage.
I know,
It's,
but
yeah.
how much more can you handle?
We didn't actually calculate
For-
we didn't calculate the values of that, but we know that our wing loading and our aspect ratio, we exceeded the minimum requirement by a little. So by since all of those involve the weight of the plane, or since the wing loading involves the weight of the plane in the calculation, we left a little leeway so you would be able to attach some more weight that would alter the gliding mechanism of the plane, how fast it would be able to fly. So we haven't calculated in detail, but there's still capacity for some more weight, a few more ounces.
Just want to know, like, how much would be the cost of, theoretically, for, like, to create such a plane like this? Because I believe that, as you said, with using it as scouting and using it with the Red Cross, you would obviously mass produce it if it passed like prototype stages.
So the cost of our plane, our prototype, was approximately $120 to $150. We used a lot of the pieces were already provided by our mentors, but the main costs come from the propeller, motor, and battery. So these have to be adjusted to the new specifications. This is only a prototype, so like Shravan said, the military could employ a carbon graphite body, which is more expensive, but also more durable and lightweight. So the cost would go up from $125 to $150, but it's a lot less than the bigger drones that they have to call in for special missions.
Additionally, it's important to keep in mind that all the pieces of this plane were hand designed, handcrafted. So the cost of a plane like this would be a lot more. However, in the future, if they were being mass produced, they would be machine produced and therefore lower the cost.
Last question.
If there's no further questions, that concludes our presentation.